Pijanowski. I'm an AI solutions engineer on MinIO's marketing team. So essentially, I am an engineer on a marketing team, which for me is kind of a fun job. I get to do a lot of research and apply what I know about AI to object storage. So today what I want to talk to you about is building a data infrastructure for AI. And specifically, I want to cover these 6 topics. So I want to start off with introducing this thing we call a data lakehouse. And then from there, I want to get into some workloads that if you get these working in your infrastructure, you're going to be in a good place with respect to AI. So specifically, there are ML ops. I'll talk about traditional AI, as well as generative AI. And I want to get into distributed training. To me, distributed training is really important. And in my opinion, and this talk is a little bit opinionated, I think distributed training, I would get that going before I even bought a single GPU. And I'll conclude this talk with a discussion of what's going on in the industry with graphic processing units. So to start off, let's introduce, like I said, this thing we call a data lakehouse. Now, a data lakehouse at a high level is one part data lake for unstructured data and one part data warehouse for your structured data. Now, this might sound like a kind of a marketing ploy. These things, both data lakes and data lakehouses, have been around for a while. So are you just putting them together, giving them a new name, and calling it something new? It's not. Specifically, the data lake has to be capable of large-scale, high-performance object storage, and our data warehouse is special. It's built on what we call open table formats. And what's especially exciting for us at MinIO is a data warehouse built on top of, built with open table formats can run on top of object storage. So what you have is a data warehouse. Like I said, it's on top of object storage. But what these open table formats do is they are specifications that when you implement them, they let you have SQL-like tables on top of object storage. Okay, and what I'm showing you here is the Apache Iceberg specification. There are 2 others. There's Hudi by Uber and Delta Lakes from Databricks. And again, what they do is their specifications, when implemented, they allow you to have like a relational database on top of object storage. And I won't get into all the levels here, but what's especially nice about a data warehouse built in this fashion is you get some advanced features. So think of a data warehouse where you have ACID transactions. So typically, many data warehouses don't have ACID transactions. But you also get things like schema evolution and partition evolution. So if you're doing a lot of changes to your database, you don't have to drop all your data and reload it. You also get things like time travel, and then there's also external tables. So like I said, this data lakehouse, it's a combination of a data warehouse and a data lake. So external tables allow you to connect the 2. And my favorite feature is something that I call zero-copy branching. I'll get into that in a minute, but think of zero-copy branching as Git for your data. And like I said, I'll show you that in a minute. So let's go a little bit deeper. Now, like I said, when you have this data lakehouse, you have a place where all your data can live, both structured and unstructured. So, so under the hood, you have MinIO, which could be your object storage, but you have a lot of options. So if you want to start out small, you could have one instance of MinIO, which is, and you could have all your unstructured data in which is your data lakehouse, in one bucket, and you could have other buckets that represent your data warehouse. And again, this would be one instance of MinIO. This would allow you to start out small, so you don't have to do like a big bang replacement. But then as you grow, you may want your data lake and your OTF-based data warehouse to be on 2 separate clusters so you can scale them independently. So again, with MinIO, you can do that. And what you see here is you can have one, like I said, one MinIO tenant for your data lake and another MinIO tenant which stores your data for your data lakehouse. Things get interesting is when you have when you start putting a processing engine on top of your data. So what you can do is, again, you can keep things simple. And what I'm showing you here is a processing engine on top of your data lake, which would typically run your machine learning workloads. But you also have an OTF-based data warehouse. Also comes with a processing engine that sits on top of the of MinIO, and this would be what runs your distributed SQL. So again, you could start off keeping things simple, and you have one processing engine on top of each. But if you wanted to, you could really pull that apart. And so what's nice about the OTF-based data warehouses, which are running on top of MinIO here, is each department, if you wanted to, could have its own separate processing engine to run its workloads. So this is kind of interesting because you wouldn't have different departments clashing with each other for maybe month-end reports. And you could also use an architecture like this to do chargebacks if you wanted to keep track of which department was putting different workloads on your environment. So that's really our at a high level. That's our data lakehouse. I want to get into a little bit of machine learning operations. So we're now kind of getting into the workloads that are closer to machine learning. So when we talk about machine learning operations, it's important to understand the difference between training a model and building traditional software. And in many ways, they're almost exactly the opposite. When you build traditional software, you usually start coding, and your database does not change. And as you code, you build unit tests and end-to-end tests to judge the quality of your code. And coding is the main activity. When you train models, you really don't write a lot of code, and your data is always changing. And experimentation is the main activity. So as you're building your models, you want to keep track of all your experiments. So for this reason, you really need something different from DevOps to manage your machine learning as you build your models. And like I said, at MinIO, I've done a lot of research into different MLOps tools. I'm going to show you like 3 examples in a minute. I'm going to cover MLflow, I'll cover Kubeflow, and another tool called MLrun. But before I do, I want to just present to you like what I think are the 10 main features of an MLOps tool. And this is like a superset of my research. So to start off with, I think an MLOps tool should come from a major player. Like this space is changing all the time, so you want a major player that's going to keep your MLOps tool up to date. And as a concrete example, a lot of the tools I'm going to present to you started off before large language models were really popular. So a lot of these tools are now kind of revamping, and they're coming up with new capabilities so that you have a tool for large language models. I would say that 3 and 4 are probably the most important. As you're building your models, you want to have a tool that is going to track your experiments. So I consider those to be most important. And as you get farther on down the list, these are things you may need. Some tools have actually provided a runtime environment for you, and then other tools have ways for you to manage your completed models. And those may be things you may or may not need. So let me just go through and give you some concrete examples. The first one I want to present is MLflow from Databricks. So they set out, and a good way to understand these tools is to understand what they set out to do. So MLflow, they set out to be the best tool for experiment tracking, and that's what they do well. So it's very little code. Once you get it up and running, you can just instrument your code, again, with not writing a lot of code, and you can keep track of all your experiments. And when you're done, you have a nice dashboard where you can plot different features of the results of your models and see which features, which techniques are making your models more and more accurate. And they've done that really well. I will say, too, that all of these tools that I'm presenting, so MLflow, Kubeflow, MLrun, they all use MinIO under the hood. So think of your MLOps as really requiring that data lake side of the data lakehouse. All right, so as you do your experiments, you're generating you're generating new models. You may be versioning your data sets. All of that, the different versions of your data set models, are going into MinIO into the data lake side of your data lake house. MLflow, they do not do a lot with a runtime environment, and they have some tools for tracking your models and deploying your models. The next tool is Kubeflow from Google. Now, Kubeflow, they set out to democratize Kubernetes for ML engineers, and that's what they've done really well. So if you have a Kubernetes cluster, you can, again, install Kubeflow very easily into it. It's also going to install MinIO into a few of your pods. And what they've done is they set out to make it really easy for you to have a place to train your models. And it's very easy to do. They have 3 ways you can package your code. There's this concept of hermetic functions, where it's just a very simple function. You just throw a decorator on it, and Kubeflow will take care of taking that code and putting it into your cluster and running it. If you have other tools and you want to take more control over building out the container, you can use Python containerized Python containers and have more control over the code that gets put into that container and then moved into your cluster for training. And then finally, if you have existing containers that are not based on Python, they have a tool for that too. They do some experiment tracking. In my opinion, it's not as good as MLflow. And they do have a few tools for like a model registry and for deploying your models. The third tool I'll present to you is MLrun. Again, they run also prefer to run in a Kubernetes cluster, and they'll install MinIO for you. But what MLrun, they are from a company known as Aguazio. It's an Israeli-based company that was recently acquired by McKinsey & Company. And what they set out to do was to eliminate all boilerplate code. So think of just having a tool set where you can put decorators on your code. They have a lot of functions. And when you really come up to speed on this, you'll be surprised at how little code you have to write. You're pretty much just focusing on your model architecture and just handing your model off to MLrun to get trained and tested. And they've done that really well. They've used a third-party product known as Nucleo for their runtime environment. But if you want, you can also use Kubeflow. So there's a little bit of integration, Kubeflow pipelines, and you can mix and match as you see fit. So again, those are the three. And I really don't have any particular one that I like to recommend. I always think that you have to know your environment. You have to know what you want to do. If you already have a runtime environment, you're comfortable with that. Maybe an MLflow will work for you. If you're really just starting out, maybe you consider an MLrun because again, once you learn their tools, it can be very efficient. Let's move on and talk about the actual AI. I like to think of AI as coming in 2 flavors. There's the traditional AI, which is everything that was around before ChatGPT. And then there's generative AI, which, as you know, is for generating new content. Think of traditional AI as the regression, classification, categorization. Those type of models. And I like to call them out because they each put a very different workload, or they use very different workloads in your AI infrastructure. So to start off with, let's talk traditional AI. With traditional AI, chances are you're dealing with a little bit of structured and unstructured data. So obviously, your unstructured data will go into the data lake side of your data lake house. This might be things like images, audio files, etc. And that's where you'll point your training clusters to and use the data lake. But if you have structured data, such as maybe Parquet files or Avro files, you can also put those in your data lake. But you have an option. Those tools can very easily be ingested into your OTF-based data warehouse and used by other teams like analytics teams, data science teams. And so now you have a situation where that data can be used in a more widespread fashion throughout your organization. If you do end up putting data into your OTF-based data warehouse for machine learning, what's nice is these type of data warehouses come with what's known as zero-copy branching. Like I said before, that's Git for your data. So let's say you want to do, I think it's very powerful for feature engineering. Let's say you wanted to just walk up to a couple of tables and you wanted to tweak them, change the features a little bit. You can make your own branch of the database. Now, under the hood, you're really not making a whole other copy. You're just getting another copy of that metadata layer that I showed you, and then you can do whatever you want. If you run an experiment and you don't like the results, you just throw away your branch, just like you would with your software. If you run an experiment and you like it and you want to share it, you can merge it back into the main branch. If by chance you mess something up and you want to go back and undo something that you merged, you can do that as well. So again, this is known as zero-copy branching. It's probably one of my favorite features for OTF-based data warehouses. So let's move on to generative AI. Like I said, this puts a different workload on your AI infrastructure. And if you are serious about generative AI, probably the first thing you're going to want to do is build a document pipeline. And to do this, you'll probably use object storage like MinIO to build out a custom corpus of the documents that your organization owns that represents your own proprietary IP that you think are important enough to participate in generative AI. And this could potentially be the hardest part of a generative AI solution. You have to go through all the portals in your organization, figure out which documents are correct, represent the facts of your company, and most importantly, as you move those into your custom corpus, you want to keep track of access rights for those documents. You don't want to, you want to make sure that as you build out your generative AI, you honor the authorization and access rights of those documents, and you can do that with retrieval augmented generation within generative AI. So at the end of your document pipeline, you'll be building out a vector database. Again, this is a very important part of generative AI, and this is this will basically be your start. This is your document pipelines. Once you just in case you may be unfamiliar with vector databases, they're a new type of database, and they facilitate what's known as semantic search. So unlike a traditional database, this is what you're seeing here is a search that would have to be applied to a normal relational database if you're storing text documents into it or chunks of text into it. And you can see here, if you want to do a search for artificial intelligence, you would have to know every synonym of the term you're looking for, and you'd have to build out a very long, complex query, and it's prone to error, and it'll probably run slow. What vector databases do is using dirty little tricks of mathematics and vectors, is they understand semantic meaning of the chunks that you put in them. So you could do a search like this, and the vector database will take care of making sure that anything related to your search term, even if it's an abbreviation or just a synonym or what have you, is going to come back in your results. Okay, so that's our vector database. Now, one of the more important workloads you probably want to build out if you want to do retrieval, if you want to do generative AI, is retrieval augmented generation. And what you're seeing here are the subsystems of retrieval augmented generation. There's your document pipeline, which I just showed you. There's also the building out of your vector database, and then prompt engineering, and then inference. So all these things you'll want to build out. If you're kind of unfamiliar with retrieval augmented generation, it's a technique whereby you can use that custom corpus that's in your vector database to enhance the results to enhance the prompt that goes to the large language model and get information that is not really baked into the parametric memory of the large language model. The other thing you can do, too, is you can use that same custom corpus to fine-tune your models. Now, with fine-tuning, you take an already trained model and you train it a little bit more with the information that represents your the documents in your custom corpus. Most people don't do this, and most people think it's either or. You either do RAG or you do fine-tuning. But a clever trick I've noticed that some customers do is they'll start off with a proof of concept, maybe using ChatGPT's APIs. They'll build out their custom corpus. They'll get their RAG workflow working, and then they'll use the public APIs to see if they can get a viable result. Then to have something that runs a little bit cheaper, they'll get a cheaper model, fine-tune it with their custom corpus, and then run it on-premise so that they have more control and can and do more with it. Okay, so again, for generative AI, it's really your RAG workflow, your fine-tuning workflow, and your document pipeline. So let's talk quickly about distributed training. So again, what I do, a lot of what I do at MinIO is I kind of think of things that our customers might be struggling with using object storage and all the tools that also rely on object storage. One of the things I did several months ago is I put together, I kind of gave myself a challenge. I wanted to train a model on a data set that could not fit into memory, or furthermore, couldn't fit onto the hard disk of a single server. Okay? I wanted to train it. I wanted to train a model in a distributed fashion. I had some pre-processing to do. I wanted to do the pre-processing in a cluster in a distributed fashion. I wanted to checkpoint my model every epoch because I didn't know if I was going to crash. I wanted to pick up where I left off. And I wanted to use MLflow to keep track of my experiments. Okay? So I put all this together. I put it together with MinIO, MLflow. I use the Ray framework. And what you see here is, you see a link on the bottom. That's a link to one of my blog posts. I put all that code together, and it makes a big difference. So sometimes engineers are used to just putting together scripts that just run top down. But when you do get something like this working, and you are able to deploy it on a cluster, your experiment time is greatly reduced. And the rule of thumb with training models is the more experiments you can do, the more accurate your model will be. So for that reason, I really recommend trying to get distributed training working before you even buy a single GPU to try to speed up your training, because it could be that your cluster of CPUs is all that you need. And a lot of times with frameworks like, again, I use the Ray framework from AnyScale. A lot of times once you get your code working in a distributed fashion, it's just a configuration change to switch it over from CPUs to GPUs. I also did a similar thought experiment with building out a vector database. So what you're seeing here is, again, this is a similar graphic to what I just showed you. The RAG has basically 3-4 subsystems. I'm in the process of moving all of those to writing posts and white papers on moving all of those to a distributed cluster. And again, what I did here is I set up an experiment where I could build out my vector database in a cluster. And that's important because you're going to be rebuilding your vector database over and over as you fine-tune your retrieval augmented generation workload. All the different parameters, like how big your chunks are going to be, the chunk overlap, et cetera, all those things you have to experiment with. There's no best practice that applies to everybody. So again, more experiments, the better your ML will be. And finally, last part of my talk, I wanted to just kind of go quickly over what's happening with graphic processing units. Now, what you see here is a list of all the GPUs from NVIDIA. And what's interesting is, let's focus on the performance. And you can see that every time NVIDIA changes their architecture, and they name their chips after mathematicians. So we have Ampere, Grace Hopper, and Blackwell. But every time they change architectures, it looks like it's around, maybe it's a little bit more than 2x or a little bit less than 2x. So there's a kind of a little bit of a Moore's Law thing going on with the GPUs. So you can see, again, what's interesting is when I first did this talk maybe 6 months ago, I had this slide in terms of teraflops. When NVIDIA announced the Blackwell chip, I had to beef it up and make it in terms of petaflops. So, but it's not only the performance that's really increasing. Look at what they're doing with memory. So they're really making big improvements on the amount of memory that's on these GPUs as well. And as you know, the memory on the GPU dictates your batch size. So not only are these GPUs getting faster and faster, but they're also chunking through your epochs at a higher rate. Okay? And finally, you can see that, well, the costs that I have here, those are rough figures. It seems like every time I query the internet, I get a different price. But you can see these GPUs are expensive. They are not cheap. And just to call out some work that some other companies are doing, if you follow Intel, what they're doing with their Gaudi accelerator, they call it an accelerator, is that's coming in, it's not as fast as NVIDIA, that's coming in about as fast as the Grace Hopper. So look at the H100, H200. That's what you're going to see from Intel, but they're going to compete on cost. So they won't be as fast as NVIDIA, but they're going to be probably roughly half the cost. And that's an interesting way for them to compete. You don't always have to have the fastest, but you can have the best price for your accelerator. So what's interesting about the trend in GPUs is it's really getting a lot faster. And just for fun, I kind of charted out. So in case you wondered, a petaflop is floating point operations per second. Okay, a petaflop is 1 with 15 zeros after it. And this is how many floating point operations happen in 1 second. So look at your watch 1 second tick by, and that's how many operations are happening. That's pretty crazy. You can see that the Blackwell 200 is doing like 4.5 petaflops. That's, like I said, that's a crazy amount of processing. And when you apply this to your data infrastructure, it gets really interesting. So, and you really have to think this through if you really want it to work. So let's say you have, let's say you're just going to buy some GPUs and just shove them into your existing infrastructure. Well, you may want to think about that. What could happen if you're in a situation like this where you have maybe just an average network, object storage, that would be MinIO, and you just have the best GPUs money could buy. Well, your GPUs are going to be the fastest thing in your infrastructure, and that's really not what you want. They're going to be underutilized. The network won't be able to keep up. Object storage may not be able to keep up. And you'll have underutilized GPUs, and you won't be able to do anything about it. And that's not what you want. If you spend that much money for your GPUs, you want to keep them as close to 100% utilized as possible. So, like I said, at MinIO, we think about these things all the time. We do have some new features in our, presently we call them our enterprise offerings, but we have a cache. So think of a cache as something you can turn on at the bucket level. And the way it works is that's all you have to do. You turn it on to bucket level, and we do all the work for you. You'll frequently accessed objects will go into the cache. So think of your model training loop. You're going through all your epochs. That first loop will put all your objects in the cache, and after that, they'll just get served right up from memory. And this is an interesting use of the servers that we run on. What we've noticed is that when customers buy servers for MinIO, is a lot of times the memory goes unutilized. So we can pool all that memory together, package it up as a very durable cache, and again, you don't have to do anything. You just turn it on. It just works. And like I said, like normal caches, a lot of times with normal caches, you have to check the cache yourself. If it isn't there, you go get it yourself and then put it into the cache. You don't have to do that with ours. Like I said, it just works. And so that's really everything I wanted to tell you today. Looks like I'm right on time. I did cover a lot of things. We went over the data lakehouse. I went over all the workloads for AI/ML, and finally discussed GPUs. I do have a lot of white papers. Everything I showed you here today comes from a blog post or white paper that I've written. So this was more of like a summary. So again, hopefully you'll be able to download these slides, and you can check out all this information in more detail. And that's everything I had for you. Thanks for your time. Enjoy the conference.